Welcome back, focused learners, to another explainer. Today, we're cracking the code on what I think is one of the most fascinating chemical competitions out there. Now, we've previously looked at how passing an electric current through a molten compound splits it into its basic elements, right? That's standard electrolysis. But today we're turning up the complexity. We're looking at what I like to call the battle of the ions, aqueous electrolysis. So get ready, because the rules of the arena are about to change entirely. So think about when we deal with insoluble compounds, like metal oxides. We literally have to melt them into a molten liquid just to free up their ions so they can move around and conduct electricity. In that scenario, honestly, it's pretty simple. You only have two ions to worry about. But for soluble compounds, things like copper sulfate or sodium chloride, we can take a much easier route. We just dissolve them in water to make our electrolyte. But here's the catch. Adding water doesn't just dissolve our compound. It introduces a whole new set of competing ions into our chemical arena. Suddenly, the dance floor is very, very crowded. Okay, let's dive right into this. Here's our game plan for today. We'll start with the aqueous complication, then we'll look at the cathode and its reactivity rule, followed by the anode and the halide hierarchy. After that, we're putting it into practice. And finally, we'll wrap up with identifying the winning gases. Let's kick things off with Section 1, the aqueous complication. Water joins the mix. Now, an aqueous solution simply means a solution where water is present. Pretty straightforward, right? But in chemistry, water isn't just some neutral bystander taking up space. In an aqueous solution, the water molecules actually split apart, or dissociate, into two distinct ions: positively charged hydrogen ions and negatively charged hydroxide ions. So instead of just having the positive and negative ions from our dissolved compound, we now have 4 total ions swimming around in our electrolyte. And they are all competing to react at the electrodes. And this brilliantly illustrates exactly what that crowded arena looks like. Here we have a classic electrolysis setup. It's a beaker full of an aqueous sodium chloride solution, which you probably know better as brine. We've got our 2 inert electrodes made from something unreactive, like platinum or graphite, and they're wired up to a power supply. If you look closely at the magnified circles, on the left side, by the negative cathode, we don't just have sodium ions. We have sodium ions competing right alongside hydrogen ions from the water. And on the right, by the positive anode, we have chloride ions competing with hydroxide ions. 4 ions enter, but only 2 can actually be discharged. Moving on to Section 2. Cathode, the reactivity rule. The strict judge. Okay, so the cathode has a negative charge. That means it naturally attracts the positive ions in our solution. So the metal ion from our dissolved compound and the hydrogen ion from the water are both going to race toward it. But the cathode, it's picky. It will only discharge one of them. The absolutely crucial point to remember here is this: the cathode acts as an incredibly strict judge, and its core rule is that the ion of the least reactive element gets discharged. Think about that for a second. The underdog actually wins the battle. Let's look at how this reactivity rule actually plays out with a couple of real examples. If we dissolve copper sulfate in water, the cathode has to choose between copper ions and hydrogen ions. Well, if we check a standard reactivity series, we find that copper is actually less reactive than hydrogen. Because copper is the weaker, less reactive element, it wins. The copper ions are discharged, they gain 2 electrons, and they form pure, solid copper right there on the electrode. But what if our solution is sodium chloride? Now the cathode is choosing between highly reactive sodium ions and hydrogen ions. Because hydrogen is much less reactive than sodium, the hydrogen ions take the win. They're discharged, gain electrons, and bubble off as hydrogen gas. Let's flip over to the other side for Section 3. Anode, the halide hierarchy. Rules at the anode. So, the anode has a positive charge, meaning it attracts all the negative ions, the non-metal ion from our compound and the hydroxide ion from the water. But the anode doesn't really care about reactivity in the same way the cathode does. Instead, it operates on what's basically a VIP guest list system. I like to call it the halide hierarchy. Here's how this hierarchy works. The anode always checks the door to see if a halide ion is present. Halides are ions from the halogen group on the periodic table. So we're talking about things like chloride, bromide, or iodide. If a halide is in the solution, boom, it gets VIP priority. It gets discharged, loses its extra electrons to the anode, and forms a halogen gas like chlorine or bromine. But If a halide isn't present, say we have a nitrate or a sulfate ion instead, then it's always the hydroxide ion from the water that gets discharged. And when those hydroxide ions give up their extra electrons to the anode, they react to form oxygen gas and water. All right, section 4, putting it into practice, predicting outcomes. Before we look at the results, let's just lock this comparison into our memory, because the structure is actually quite elegant. At the cathode, it's a battle of the positive ions, and the least reactive element wins. At the anode, it's a battle of the negative ions, and halides automatically win if they're present. If they aren't, hydroxide steps in to produce oxygen. Understanding these two frameworks, that's literally the master key to unlocking aqueous electrolysis. Now, what's really interesting here is how clearly this acts as a results board for our chemical battles. Let's trace the logic together. For concentrated sodium chloride, the anode sees a halide, chloride, so it produces chlorine gas. The cathode sees sodium and hydrogen. Well, hydrogen is less reactive, so hydrogen gas is produced. Simple enough. In our second example, aqueous copper sulfate, the anode sees a sulfate, which is definitely not a halide, so hydroxide takes over and produces oxygen gas. Meanwhile, the cathode sees copper and hydrogen. Copper is less reactive, so solid copper is produced. And for dilute sulfuric acid, there are no halides, so the anode gives us oxygen. And since the only positive ions in the whole mix are hydrogen, the cathode simply produces hydrogen gas. Now, you might be wondering, why does any of this matter outside the lab? Well, electrolyzing concentrated sodium chloride, which is really just salt water or brine, is actually one of the most important industrial processes in the entire world. That chlorine gas bubbling off the anode, we harvest that to make bleach. The hydrogen gas bubbling off the cathode, we capture it to manufacture margarine. And remember, because the sodium and hydroxide ions were the losers of their respective battles, they just remain behind in the solution, forming sodium hydroxide. We actually collect that leftover solution to manufacture the soaps and detergents you use every single day. This simple battle of ions literally makes modern hygiene possible. Okay, finally, section 5, identifying the winning gases, lab tests for winners. So if our anode rules tell us that no halides were present, we expect oxygen gas to form. But how do we prove it? We collect a sample of the gas in a test tube. Then we take a wooden splint, light it on fire, and blow it out so it's just glowing hot embers. When we dip that glowing splint into a test tube full of pure oxygen, whoosh! The sudden abundance of fuel causes the splint to instantly burst back into flames, relighting completely. If it relights, you've got oxygen for sure. But what if we had a concentrated halide solution, like our brine, and we expect chlorine gas at the anode? Well, chlorine is a powerful bleaching agent. To test for it, we take a piece of blue litmus paper and make it damp. When we hold it near the anode, the chlorine gas will first react to turn the blue paper red because the solution becomes slightly acidic. But then, almost immediately, the powerful bleaching action kicks in and strips the color away entirely, turning the paper stark white. And finally, if our cathode rule tells us that hydrogen won the battle because the competing metal was too reactive, we get to perform arguably the most famous test in chemistry. We collect the gas in a test tube and bring a fully lit splint right to the open mouth of the tube. Hydrogen is highly flammable, so when that flame hits the concentrated hydrogen, it ignites rapidly with a very distinct, high-pitched, squeaky pop sound. If you hear that pop, you know exactly which ion won at the cathode. And there you have it. By understanding that strict least reactive rule at the cathode and the halide hierarchy at the anode, you can confidently predict the outcome of almost any aqueous solution you encounter. You've officially decoded the hidden chemical competition happening right inside the beaker. So the only question left is, now that you know the rules of the arena, what will you electrolyze next? Thanks for joining me for this explainer, and I'll see you next time.